Okay, G8B, frequency mixing, multiplication, HF data communications, bandwidths of various modes, and deviation. What receiver stage combines a 14.250 megahertz input signal with a 13.795 megahertz oscillator signal to produce a 455 kilohertz intermediate frequency IF signal? Now, forget the numbers for a minute. Okay? What receiver stage combines? If I show this to someone who doesn't know a thing about radio and they see what receiver stage combines and they look down here at the possible answers, what are they going to say? Well, if you're going to combine it, you're going to use a mixer. Okay, and that is the case in this this question. Now, let's come back and look at the numbers, though, so you can see what's happening here. Here's a block diagram of what they're talking about. We have a receiver, and you may recognize this from last time when we had the question about what's the simplest kind of super heterodyne receiver you can have, and this block was X'd out in red, and this block was X'd out in red, and that was the simplest kind you could have. Now, here we have coming into it the signal that we want to hear at 14.250 megahertz. We have an intermediate frequency amplifier, and these intermediate frequency amplifiers have very narrow filters in them that will give only the audio bandwidth at the intermediate frequency, which in this case is 455 kilohertz or 0.455 megahertz. Okay? In order to get the signal that I want to my intermediate frequency signal, I mix it with a local oscillator signal that is different from this signal by this amount. Okay? So to get my 455 intermediate, I mix this with this. One of my mixer products is this minus this, which gives me this. Okay? That's what's happening here in the mixer, and this is how I get my intermediate frequency that I can continue on down through the receiver here and continue to process. A mixer is a circuit that changes the frequency of an electronic signal. A mixer produces outputs that are sum and difference of the input frequencies. In most mixer designs, the input frequencies are also present in the output. Let's just take a look at the simplest case, that our desired outputs here. We have an input here, input A, and input B going into the mixer, and then we have an output, which is A plus B. These are frequencies now. The frequency of A plus the frequency of B, and then we have A minus B, the frequency of A minus the frequency of B. Or if input A is 14 megahertz and input B is 10 megahertz, our outputs are going to be 24 megahertz A plus B and 4 megahertz A minus B. Okay, so that's what a mixer does. Now, in most mixer designs, you're going to have the other two frequencies coming on through. They're not being acted on in the mixer. They're just coming on through the mixer along with these other products. Okay, so in addition to the 24 and the 4, you'd also have the 14 and the 10 that you put into it, and you can deal with those by additional processing. If a mixer mixes a 13.800 megahertz VFO with a 14.255 megahertz received signal to produce a 455 kilohertz intermediate frequency signal, what type of interference will a 13.345 megahertz signal produce in the receiver? Let's go straight to the diagrams and take a look. Okay, here we are with the same diagram, a little bit different numbers on it. Now, the 14.255 is the signal that we want, and our intermediate frequency is at 0.455 megahertz or 455 kilohertz. Okay, so we can get that by putting a 13.8 megahertz signal into the mixer. The difference between 14.255 and 13.8 is our desired intermediate frequency of 0.455. But there's something else that can happen here. Let's take a look at the next slide. there's something called image response. And here's the signal that I want to come through, but my VFO signal, my 13.8, can also mix with 13.345 to give me an intermediate frequency of 455 kilohertz or 0.455 megahertz. Okay? So I can get an image frequency coming through also. And that's what this is image response. Let's take a look at the block diagram again. And here we can see what I just showed you in that other thing. If a signal at this frequency gets into my mixer, it will produce the image. Now, remember I told you last week that that very simple superheterodyne receiver we were looking at was a bad design. This is why. Because there was nothing to keep this image frequency out of there. Okay? And one of the main purposes, or one of the important purposes, of a tuned radio frequency amplifier in front of your mixer is to not be tuned to an image that would be undesirable for the receiver. So part of the function of the tuned radio frequency amplifier, in addition to boosting the level of the signal, is to block out the image frequency. Okay? So what type of interference will this other signal produce? It'll produce an image response in the receiver. What is another term for the mixing of two radio frequency signals? It's called heterodyning. It's just a definitional thing. Don't try to make sense out of it. Just know that that's what the mixing of two RF signals is heterodyning. What's the name of the stage in a VHF FM transmitter that generates a harmonic of a lower frequency signal to reach the desired operating frequency? Let's take a look at the block diagram and see what it is they're talking about here. Especially in some of the older FM transmitters, when FM was new in ham radio, they would use a low frequency or a relatively low frequency oscillator, and then they would have a multiplier chain that would bring the frequency up to what you wanted your operating frequency to be. Now, these frequencies aren't amateur frequencies, but the principle holds true. Here we have an oscillator operating at 18 megahertz. Okay, and here we double it to 36 megahertz, and here we have an intermediate amplifier that is going to boost the signal level, and then we have another doubler that doubles the 36 to 72, and then we have a tripler and power amplifier that triples the 72 to 216 megahertz, which is our desired frequency, and then boost the power up to where we're ready to put it into an antenna. Okay, that's the stage that generates the harmonic to reach the desired operating frequency is called a multiplier, and it was typically used in multiplier chains like this of doublers and triplers to bring the signal to the operating frequency that was desired. Why isn't frequency modulated phone used below 29.5 megahertz? The answer is that the bandwidth is wider than the FCC allows below that frequency. The FM bandwidth is prohibited by the FCC below the 29.5 megahertz frequency. What's the total bandwidth of an FM phone transmission having a 5 kilohertz deviation and a 3 kilohertz modulating frequency? Okay, we're looking now for the total bandwidth of this signal. We have 5 kilohertz deviation and a 3 kilohertz modulating frequency. Let's take a look at what's going on here. The 5 kilohertz deviation is 5 kilohertz to each side of the carrier. So we're already with a bandwidth of 10 kilohertz wide with the 5 kilohertz deviation of the signal. Okay? And then the 3 kilohertz modulating frequency includes the increases the bandwidth by 3 kilohertz on each side of the carrier, making the total bandwidth 2 times the deviation plus 2 times the modulating frequency. Okay? So for a 5 kilohertz deviation and 3 kilohertz modulating frequency, we have twice the deviation plus twice the modulating frequency, or 10 kilohertz plus 6 kilohertz is 16 kilohertz. Okay, what does that mean? For a carrier frequency of 146 megahertz, the bandwidth would be from 145.992 to 146.008. That would be the actual bandwidth of that signal, based on around a 146 megahertz carrier frequency. What is the frequency deviation for a 12.21 megahertz reactance modulated oscillator in a 5 kilohertz deviation, 146.52 megahertz FM phone transmitter? Let's take a look at the block diagram on this and find out what's going on here. What we have is a transmitter that has an oscillator or a multiplier chain like we just looked at in the other question. Here we have a reactance modulator that is applying frequency modulation to the oscillator. And since it's applying it to the oscillator, this will be true frequency modulation, won't it? Okay. Now, how do we know what these multipliers in here are? Okay. Well, we know that we have an oscillator operating at 12.21 megahertz, and we have an operating frequency here coming out of the tripler, going into the power amplifier, of 146.52. Okay, so if we divide the 12.21 megahertz into the 146.52, we will find that the operating frequency is being multiplied by 12 times. In other words, the oscillator is being multiplied by 12 times to get to the operating frequency. Okay, now so we know that we have to have a doubler and a doubler and a tripler to give us 12 times multiplication. So here, my oscillator frequency is 12.21. We know that because they told us that. My doubler frequency is twice that, 24.42. We know that because that's double this. Here is our second doubler, 48.84. And here is our tripler, which brings us to 146.52. Now, since we have frequency modulation, every time we double the frequency or triple the frequency, we also double or triple the deviation. So here I had this deviation, here I had this deviation, here I had this deviation, here I had this deviation. Okay, now to find what this deviation is, I take the one they give me, the 5 kilohertz, divide it by the 12, and I get this. Okay? So you don't really have to go through all of the gyrations that I just went through there. Once you know that your multiplication is by 12, you can just take your 5,000 hertz of deviation, divide it by 12, and there you are right there. Why is it important to know the duty cycle of the data mode you are using when transmitting? Some data modes have high duty cycles, which could exceed the transmitter's average power rating. In other words, some of them have long transmit times. Radio teletype is a good example of that, or slow scan TV is a good example of that. And so you have to turn down the power on your transmitter so that you don't exceed the transmitter's average power rating and damage the transmitter. So that's why it's important to know the duty cycle of the data mode you're using so that you don't exceed the transmitter's average power rating. Why is it good to match receiver bandwidth to the bandwidth of the operating mode? Let's take a look at what they're doing, what they're talking about here. Here are filters in a receiver. Okay, here's a broad filter, or a broad bandwidth in the receiver. Here's a narrow bandwidth in the receiver. Okay, here is our desired signal, this green thing. All right? Now, along with that desired signal, there's a whole bunch of noise here, okay, that we receive along with that signal. If we narrow the bandwidth of the intermediate frequency, or narrow the bandwidth of the receiver to the same as the desired signal, then we'll get the best signal to noise ratio because we'll be cutting out this other noise over here. What does the number 31 represent in PSK 31? The 31 is the approximate transmitted symbol rate. Approximately 31 symbols per second can be transmitted in this symbol rate. How does forward error correction allow the receiver to correct errors and receive data packets? They transmit redundant information along with the data. Let's take a look at a diagram of that. Here's the packet that you type into your packet keyboard. Okay, the terminal node controller packages it up like this. Okay, and they put in redundant bits that duplicate each other. Okay, now some of those bits get lost in transmission. There's enough left on this end for the receiving processor to be able to reconstruct the packet. Okay, if it can't reconstruct the packet, it will be asked to have it sent again. But forward error correction sends enough redundant packets that usually the receiving processor is able to reconstruct the packet from the redundancies in the transmitted data. What's the relationship between transmitted symbol rate and bandwidth? The correct answer is higher symbol rates require higher bandwidth. And we took a look at the maximum legal symbol rates a while back in one of the other lessons, and you'll remember that down in the lower frequencies, they have the lower symbol rates of 300 bits per second. And then once we got up into the higher ones, and once we got up into the up above the UHF, the rates were unrestricted because up there's more bandwidth to work with. So the higher symbol rates require a higher bandwidth or a wider bandwidth.